All right, what's up, ladies and gents? 9-4 limit comparison. We talked about direct comparison last section. In this section, we're going to talk about the limit comparison test. So some series closely resemble others, but you are unable to apply the direct comparison test. Remember, we had to find something that was very similar or kind of reacted similarly in the last section. And then if this is the case, then there's a second comparison test called the limit comparison test. Okay? And so here's a nice example of a series here, and it's a good example of where direct comparison will not work, but limit comparison will. And so we talked about in the last section like P series and other things like that. I mean, we could technically use it. So this, like a direct comparison, would be like 1 over the square root of n, right, from 1 to infinity. And 1 to n, 1 over the square root of n is actually going to be greater than 1 over 2 plus the square root of n, just because of the values that n could be, right, from 1 to infinity. And we know this is probably going to converge, right, and then therefore this is going to converge as well. But direct comparison and things that are a little bit different than this or whatever, they might not be exactly as good as this one. Like if it was the square root of n minus 2, okay, then I could not use the actual direct comparison with the like diverge or converge piece, because the square root of n is definitely less than 1 over the square root of n minus 2. And so this is probably going to not converge. This might go into diverge and stuff like that. So we are going to use the limit comparison, right, and show you some other new test to kind of work on. So let's get to that. So if we look at the limit comparison down here, we basically are going to come up with two different individual pieces, two series, a sub n and b sub n. As long as they're greater than 0, okay, then the limit as n approaches infinity of the dividing pieces, so a sub n divided by b sub n, is equal to some L. L is the limit where it's finite and positive. So if it's negative, then we don't know what's going on. If it's infinity, then that's not good either, right? So what we're going to do is we're going to be given a series, so kind of like what we are down here, and we are going to use that series to compare with another series that reacts similarly. Just like we did in the last section, we found series that were similar, and I want to then do my limit comparison test. So let's actually get going with that. So what we're doing is, all we're doing here is just finding a thing to compare. So we're looking at the bottom, and 3n squared minus 4n plus 5. Well, if I look at the bottom, like that's really the only, because of the 1 on top, we don't really care about that. What's actually kind of, I guess, growing or decaying or whatever? Well, it's really this n squared term. So I can compare this to just 1 over n squared. Okay, because that's really the thing that is growing. That's everything else here is going to be arbitrary. Okay, this one over here, this is really going to be probably compared to the 1 over the square root of n. Because again, the square root of 3, like that's arbitrary. This minus 2, it just doesn't really do much at infinity. So the thing that cares is the square root of n there. Well, what about this here? We know the bottom is kind of going to be acting like the square root of n, but the top is going to be acting like n squared. So n squared obviously is going to grow probably faster, but if we look at this, I want to find something to compare it to. We know that this here is n to the half. So if I compare and I kind of break down some things, this I can compare to n to the 3 halves. Okay, this is something that I can compare it to n to the 3 halves there. And you can actually think about 2 over a half, like I canceled out, right, and 3 halves is what I get. This one here, I can probably, right, compare it to 1 over 2 to the n. Because, again, the minus 1 at infinity is going to be so negligible that it doesn't matter. So 1 over 2 to the n on this piece. So let's get into some examples now of how we can actually use what we're doing here, the limit comparison test. And so we need to find a fraction, right, that is easily compared to this. So I can probably compare this to the square root of n over n squared, right? This plus 1 here is arbitrary. It's negligible at infinity. So if I do this, this is going to be 1 over n to the 3 halves, right? This is n to the 1 half. When I reduce, I get 3 halves in your denominator. So I'm going to compare it to 1 over 3 halves. So this is my new a sub n, okay? A sub n. What I want to do now is, this is our b sub n. We're going to say that this is our b sub n here, okay? My new function that I'm comparing it to is always going to be my a sub n. So let's make it just clarify on that. My new function that I'm going, or my new series that I'm going to compare it to is a sub n. So what I want to do is I want to now use the limit comparison test. I want to say, okay, the limit as n approaches infinity. Remember the limit comparison test was a sub n over b sub n. So a sub n is, I'm gonna actually not use this. I'm gonna use this piece right here. It just makes it a little bit easier. I'll explain why. So that's n square root of n over n squared. So that's a sub n divided by b sub n. Okay, and b sub n is the original function. I know the plus 1 is arbitrary at infinity, but that's what we're going to do there. Well, this is actually equal to the limit as n approaches infinity of the square root of n over n squared times, now I can flip this as the reciprocal, right? N squared plus 1 over the square root of n. You can see that if I left it as 1 over n squared, or n to the 3 halves power, if I left that as this here, this might not be easy to kind of cancel. Okay, so that's kind of why I'm leaving it as the square root of n over n squared, even though it's the same thing. Well, that's the same, right, as the limit as n approaches infinity of n squared plus 1 over n squared. All right, hopefully we can see that. So then we have the limit as n is going to go to infinity of 2n over 2n. How did I get that? Remember, this technically goes to infinity over infinity, right? And then we have L'Hopital's rule, and then that's how I get this, which then it's going to go limit as n approaches infinity of 2 over 2. That's another L'Hopital's rule, okay, which is equal to 1. So, because the limit is equal to 1, this is a finite number and positive value. So because it's finite and positive, we have to then determine what each of these functions go to. Now, which one's going to be easier to probably deal with? It's probably going to be this one here. So this is kind of why I put it in this form. So I'm going to bring this down, and I'm going to say, okay, I have the sum from n to 1, n equals 1, to infinity of 1 over n to the 3 halves. Well, we know that this is going to converge because of the p-series test being greater than 1. All right, this is actually 1.5. So because that's greater than 1, which it is, we know that the original n equals 1 to infinity, the original series, square root of n over n squared plus 1, is going to converge because of the limit comparison. Okay, so that's what the limit comparison test says. If I have some series that I have no idea what's going on, I can compare it to some series that is similar, and then I can use the limit comparison test, divide a sub n divided by b sub n, figure out that limit. If that limit is finite and positive, then whatever a sub n does, b sub n is also going to do. All right, so let's go to another example. Let's do it. Oh, right there. All right. So I have the summation from n to 1 to infinity of n to times 2 to the n over 4n to the third plus 1. Well, I'm going to compare this to n times 2 to the n over n to the third, which actually is 2 to the n over n squared. Okay, the reason I left this n in here, because I know 2 to the n is actually going to grow by a heck of a lot more, but really you're still comparing, like this is still a comparison. It's nice because it is going to simplify with the denominator, right? So it kind of left it in there. We got to kind of think about what is going to be easier to compare and come up with things and maybe do some fun manipulation. And so that was kind of just manipulated, right? And so then if I know this is a sub n, okay, or if this is a sub n, either one of those is going to be okay. Which one of them might be better to use? We'll figure it out right here. So the limit as n approaches infinity of a sub n, because I have n times 2 to the n and n times 2 to the n right there, I'm probably going to do this as my a sub n. So n times 2 to the n over n to the third over, now my original a sub or b sub n piece, right? N times 2 to the n over 4n to the third plus 1. That is going to be equal to the limit as n approaches infinity. And I'm going to skip a step here, right? The n, 2 to the n's are going to cancel. So I have 4n to the 3 plus 1 over n to the 3. And so now what's going to happen? Well, what's going to happen now is I'm going to actually use, I can use L'Hopital's rule a couple steps, or I can use horizontal asymptotes, which this is just going to be the 4. Okay, so I skipped a couple steps, but hopefully you can see that you get 4. This is finite and positive. So because it's finite and positive, I can use the limit comparison. Okay, and so then I can say that I have the summation of n equals 1 to infinity of our new piece, which is 2 to the n over n squared. So you can see that I'm going to leave this as my comparison, but then I'm going to probably use this one in my summation here to find out if it diverges or converges. So this is going to diverge because of because let's say of the nth term test. Because no matter what, the top is actually going to grow by a heck of a lot more, right? The top is going to keep growing, and the denominator is going to not outpace that, right? So this is going to go to infinity. Okay, if I took the, plugged in infinity, and this is going to go to infinity, but this is actually going to grow to infinity a heck of a lot faster, right? 2 to the n is going to grow faster. So because the top is going to grow faster, there's going to be no bound. And because there's no bound, it's going to diverge because of that test. And therefore, we know that our original function of n 2 to the n over 4n to the 3 plus 1 is going to diverge because of limit comparison test. Okay? Fantastic. Let's go on to the last one here, and then we'll be done with this video. All right. So we have this one here, and I'm probably going to compare it. Okay, again, this minus 2 right there is negligible. So I'm going to compare it to 1 over the third root of n squared, or n to the 2/3. Okay? And that's going to be all cool and good. All right, so let's do this. So I got the limit as n approaches infinity of 1 over the third root of n squared over 1 over the third root of n squared minus 2, which is equal to the limit as n approaches infinity of what looks to be the third root of n squared minus 2 over the third root of n squared. All right, and this one's going to look a little weird, but let's kind of do some manipulation to make sure you understand what we're doing here. So this is the limit as n approaches infinity of, but because these fractions have the same root, the third root, I can actually make it one big fraction. So this is really n squared over 2 minus 2 over n squared. But that's the same as limit as n approaches infinity of the third root of 1 minus 2 over n squared, right? I split the fraction, okay? And so then this is the limit as n approaches infinity of the third root of just 1. And you're like, well, 1? Well, it's 1 minus 0, right? But if I plug in infinity here, okay, well, let's do this. Not limit, I already plugged in infinity. So let's plug in infinity. This goes to 0, or this whole fraction here goes to 0 because n squared is crazy big on the bottom. So this is the third root of 1 minus 0, which is just 1. So because this is finite and positive, we can use that limit comparison. All right, so let's compare. So I got a summation here from n equals 2 to infinity. This is at 2, not at 1, of 1 over the third root of n squared. Well, this is going to diverge. Why is it going to diverge? Because of the p-series test. Okay, p-series, the p-value, this is actually n to the 2/3. Because this is less than 1, or less than or equal to 1, or at least that's fine. And because that's less than or equal to 1, it's going to diverge. So then we know that the original function, n equals 2 to infinity, of 1 over the third root of n squared minus 2 is going to diverge also because of the limit comparison test. Limit comparison test. Fantastic. Hopefully you enjoyed this little short video, and I'll catch you on the next one. Deuces.